Fluid flows can be classified in different ways depending on the behavior of the fluid. Based on time variation, flows are classified as steady and unsteady flows. Based on spatial variation, they are classified as uniform and non-uniform flows. Based on flow behavior and Reynolds number, flows are classified as laminar and turbulent flows. Based on density variation, flows are classified as compressible and incompressible flows. Based on the rotation of fluid elements, flows are classified as rotational and irrotational flows. And finally, based on the number of spatial dimensions involved, flows are classified as one-dimensional, two-dimensional, and three-dimensional flows. Now let us understand each of these flow types one by one. Let us first understand steady flow. A flow is called steady when the fluid properties at a fixed point do not change with time. For example, imagine observing water flowing through a pipe. Now focus on point P inside the pipe. If the velocity, pressure, density, and other fluid properties at that point remain constant with time, then the flow is called steady flow. Mathematically, we represent this as dou psi by dou t equals 0. That means the rate of change of a fluid property with respect to time is 0. In simple words, the flow pattern remains unchanged as time passes. Some common examples of steady flow are water flowing through a pipe at constant discharge and airflow over an aircraft wing during steady flight. Now let us understand unsteady flow. A flow is called unsteady when the fluid properties at a point change with time. Again, consider fluid flowing through a pipe. This time, observe how the flow pattern changes at different time instants, T1, T2, and T3. At a fixed point inside the pipe, properties like velocity, pressure, and density keep changing as time passes. Therefore, this flow is called an unsteady flow. Mathematically, we represent this as dou psi by dou t is not equal to 0. That means the fluid properties vary with time. In simple words, the flow pattern continuously changes as time progresses. Some common examples of unsteady flow are starting or stopping flow in a pipe, ocean waves, reciprocating compressors or engines, fluctuating airflow in fans and blowers, and blood flow in arteries. Now let us understand uniform flow. A flow is called uniform when the fluid properties remain the same from one point to another in space at a given instant of time. Consider a flow through this pipe. Observe points A, B, and C. At the same instant, the velocity, pressure, density, and other flow properties are identical at all these locations. That means the flow properties do not vary with position. Hence, the flow is called uniform flow. Mathematically, we write this as dou psi by dou x equals 0, dou psi by dou y equals 0, and dou psi by dou z equals 0. This means the flow properties do not change along the spatial directions. In simple words, the flow looks the same everywhere in the flow field at a particular instant. Some common examples of uniform flow are flow through a long straight pipe of constant area, flow between parallel plates, and far upstream flow in external aerodynamics. Now let us understand non-uniform flow. A flow is called non-uniform when the fluid properties vary from one point to another in space at a given instant of time. Again, consider a flow through this pipe. Observe points A, B, and C. At the same instant, the velocity, pressure, density, and other flow properties are different at different locations. That means the flow properties change with position. Hence, the flow is called non-uniform flow. Mathematically, we write this as dou psi by dou x is not equal to 0, dou psi by dou y is not equal to 0, and dou psi by dou z is not equal to 0. This means the flow properties vary along one or more spatial directions. In simple words, the flow field does not look the same everywhere. Most real engineering flows are actually non-uniform in nature. Some common examples are flow around a cylinder, flow through a nozzle or diffuser, boundary layer flow over a flat plate, flow in curved pipes, and river flow through bends. Laminar flow is a smooth and orderly type of fluid motion. Here, the fluid moves in parallel layers without mixing between adjacent layers. Observe the flow inside the pipe. The streamlines are straight, parallel, and evenly spaced. There are no eddies, random fluctuations, or cross-mixing of fluid layers. The motion is smooth, stable, and predictable. Notice the velocity profile. The velocity is maximum at the center of the pipe and decreases gradually towards the walls, forming a parabolic profile. Laminar flow usually occurs at low velocities and low Reynolds numbers. Common examples include blood flow in capillaries, slow oil flow in pipes, and flow in microfluidic devices. Turbulent flow is an irregular and chaotic type of fluid motion. Unlike laminar flow, the fluid layers continuously mix with each other. Observe the flow inside the pipe. The streamlines are irregular and fluctuating. Small rotating eddies and vortices are formed throughout the flow field, causing strong mixing of fluid layers. The velocity distribution is flatter compared to laminar flow. Turbulent flow generally occurs at high velocities and high Reynolds numbers. In pipe flow, turbulence usually begins when the Reynolds number exceeds 4,000. Most real engineering flows are turbulent in nature. Common examples include river flow, airflow around vehicles and buildings, atmospheric winds, and high-speed flow through large pipes. Compressible flow occurs when the density of a fluid changes significantly during the motion. These density changes usually happen because of variations in pressure, temperature, or flow speed. Observe the flow through this converging-diverging passage. As the fluid accelerates, its pressure and density change continuously along the flow direction. At very high speeds, shock waves may also form. Compressible flow is commonly associated with gases moving at high velocities. In general, compressibility effects become important when the Mach number is greater than 0. Unlike incompressible flow, the density here cannot be assumed constant. Common examples include gas flow through nozzles and diffusers, high-speed aircraft flight, rocket exhaust flow, jet engines, and high-pressure gas pipelines. Incompressible flow occurs when fluid density remains nearly constant during motion. Even if pressure, temperature, or velocity changes, the density variation is negligible. Observe the flow inside the pipe. Unlike compressible flow, the density here can be assumed constant throughout the flow field. This type of flow usually occurs at low speeds and low pressure variations. Most liquid flows are treated as incompressible because liquids are very difficult to compress. Common examples include water flow in pipes, rivers, and canals, oil flow in hydraulic systems, and low-speed airflow in ventilation systems. Rotational flow occurs when fluid particles rotate about their own axis while moving through the flow field. Observe the swirling motion inside the pipe. The fluid elements spin as they move forward, creating vortices and circular motion. In rotational flow, the vorticity is non-zero, which means the fluid possesses angular rotation. The streamlines are generally curved and strong swirl may be present in the flow. Rotational flows are commonly seen in cyclones, stirred tanks, centrifugal pumps and turbines, water draining in sinks, and rotating machinery such as propellers. Irrotational flow occurs when fluid particles move without rotating about their own axis. Observe the flow inside the pipe. The fluid elements move smoothly without spinning or swirling motion. In this type of flow, the vorticity is zero, meaning the fluid has no local angular rotation. The streamlines remain smooth and do not form circular loops or vortices. Irrotational flow is commonly used in ideal fluid flow analysis and potential flow theory. Common examples include ideal airflow over an aircraft wing, flow around streamlined bodies, flow through nozzles and diffusers, and uniform ideal flows. One-dimensional flow occurs when the fluid properties vary only along one spatial direction. Observe the flow inside the pipe. Here, the velocity, pressure, and other flow variables change only along the x direction while remaining uniform in the y and z directions. Mathematically, the variations along y and z are considered zero. This assumption greatly simplifies fluid flow analysis and governing equations. One-dimensional flow is commonly used in engineering problems where changes across the cross-section are small compared to the flow direction. Common examples include flow in long straight pipes, flow through nozzles and diffusers, flow in ducts, and flow inside engine cylinders. Two-dimensional flow occurs when fluid properties vary in two spatial directions while remaining uniform in the third direction. Observe the flow over this surface. Here, the flow variables such as velocity and pressure change along the x and y directions, but there is no variation along the z direction. This means the flow depends only on two coordinates. Two-dimensional flow gives a more realistic representation than one-dimensional flow while still remaining simpler than full three-dimensional analysis. Common examples include flow over airfoils, boundary layer flow over flat plates, flow between parallel plates, and flow around long cylinders. Three-dimensional flow occurs when fluid properties vary along all three spatial directions. Observe the flow through this varying pipe geometry. Here, the velocity, pressure, and other flow variables change along the x, y, and z directions simultaneously. Unlike one-dimensional or two-dimensional flow, variations occur throughout the entire flow field. Three-dimensional flow gives the most realistic representation of practical engineering flows, but the analysis becomes much more complex. Such flows are commonly studied using computational fluid dynamics or advanced experiments. Common examples include airflow around cars and aircraft, flow in turbines and compressors, atmospheric weather systems, and flow around complex three-dimensional objects. Thank you for watching this video. See you in the next lecture.